There we go. Cool. Recording. Cool. Hey, everyone. So yeah, as I mentioned, I'm going to be talking about this paper called Emergence of Maps in the Memories of Blind Navigation Agents, which is one of the outstanding papers from this year's ICLR. And effectively, this paper, one of the cool things about it is quite a different paper in the sense that it doesn't necessarily introduce like any new techniques in the space, but what it does is like explores in detail by performing a series of experiments, tries to understand a little bit more how these like simple AI agents, well, simple in terms of like there's not actually anything groundbreaking in these agents, how they learn to navigate completely new environments, new spaces. And it does so in the context of what's called like point goal navigation, which is it gets set in on a point in space in a map, and it gets so in doing so, basically what this is trying to answer is like, okay, what happens if we have if we use models that are like map free and they have like no inductive bias of any kind. So these are completely like they use feed-forward neural networks and LSTMs basically as the model. So there's no inductive bias, no sort of like trying to create like map-like behavior in these neural networks. And these have shown historically to perform very well at this task. So here it's like, okay, why do they perform so well? Can we understand what they're doing? And can we like actually do some experiments to show that they demonstrate like learning of like maps or map-like behavior as a way to like complete the task. So these are the agents they use are like blind agents. So what that means is they have like no sense of any kind apart from ego motion. So they only know their position relative to their starting points and like previous positions. That's it. So they can't see, like they have no depth of perception. They have nothing. They can just know where they are relative to like previous time steps. So effectively they're blind for all intents and purposes. Oh God, pretty slow. That's just it. Okay, cool. So I guess like to talk through like the like high level results. So what they say is like despite there being no inductive bias, them having no ways of sensing, these agents manage to, they have like a 95% success rate in navigating completely unseen environments. They perform some experiments to show that there's an existence of like remembering and memory over quite long time steps. And we'll talk through like some of the experiments they do to perform that. They also kind of exhibit intelligent behavior, or behavior that when I was reading the paper is like, oh, I guess if I was in a completely dark room, completely blind, I had no senses, I feel like I would also do that, which is like following walls or taking shortcuts and things like that. And then probably the most, for me, like the most interesting thing about the paper is this kind of like demonstration that there's an emergence of like maps in the representation of these agents, and also like collision detection. So they understand like when they collide the like spaces that they can't navigate. And oh yeah, and also that these like maps are clearly built to perform like the task at hand. So what that means is they don't, the agents are not trained in any way to build these like map representations. And so as a result, they only remember the things that are like relevant to the task, which is just navigating from point A to point B. They don't remember like detours that they take or like other areas that they explore. That doesn't help them get to like the ultimate goal. So they build map-like representations that are task dependent. So yeah, quite a few different things. I think that's what makes this a cool paper, is that they like perform lots of different kinds of experiments, and they have quite a comprehensive appendix where they describe like all the details of each experiment, which I thought is quite cool. Cool. If you do have any questions, like while I'm talking, just feel free to jump in. I think I quite like it when it's just more discussion than anything. Cool. So I think like the way the sort of background to the paper is they try to say like, oh, the way animals, like the way research has been done on animals and showing how they navigate kind of points to the fact that they build these kind of map-like representations in their head in order to navigate. And so then the question is like, do artificial forms of intelligence also kind of do the same when we train them to do these tasks? The sort of motivation is that, as I mentioned, that these neural network models built for navigation that don't have any inductive bias or any mapping modules still achieve like a really high performance in achieving the task. So it's like, how is that possible? Like, what happens? And yeah, like I said, do artificial intelligence agents learn to build spatial representations? Like I said, they're blind, so they have like they don't sense anything except the only thing they know is the change in their location and orientation based off where they started and like where they've been moving towards. Cool. So these are the like questions that they seek to answer in the paper. So A, can they perform the task with no like inductive bias and being completely blind? What can we try to understand a little bit like what enables them to have this strong performance? The third one, which is like what information does their like memory encode about the environment that they're exploring? And then the last one is like, are maps task dependent? So these representations that they build, are they dependent on like the task that they're trying to do? So we'll go through each one. So the first one, which is perhaps like the least interesting part of the paper, is the fact that these blind agents are effective at navigating through environments. So I guess to go to that into a little bit more detail, each agent has, they're like initialized in the environment in a space, they're rendered as like a cylinder, and they have these, so it's measured in Cartesian coordinates, I think, which are like, so where they start is 0, 0, 0, and then they kind of like map around. And so what they can do at each time step is they can either move forward, turn left 10 degrees, or turn right 10 degrees, and stop. And when they stop, it's like, I finished the task. And yeah, like I said, they have, they understand their relative position, and they're like heading between successive steps. And so this sometimes in other literature is referred to as GPS plus compass.
One thing that was maybe slightly missing here was I think in the appendix, that we also know the distance to the final step. I think they mentioned the appendix, otherwise the topic would go.
Yeah. Right. Yeah, that's right. So they do include in the appendix, right? That they have to include that how far they are from the as like a way for them to stop.
How do they know that? How far they are?
Did they know the end? What do you mean? They know the end goal, right?
How do you know how far you? Oh, like a distance.
Yeah. So the input into the LSTM, I think, is like the coordinates plus like it's the goal coordinates plus where you are plus the distance to the end.
You think that is actually quite important information to accomplish?
Yeah. Mm-hmm. Yeah, because they don't actually include it here, but I think they describe it later on. So they have, over the course of the paper, they define these, they use these two metrics. So the first is like the success rate, which is basically, did the agent manage to successfully navigate from point A to point B within 0.2 meters of the target? And then the second metric is the success weighted by the inverse path length, which you can think of as just like how efficiently did they get to the end goal. And what they say is because the first metric is usually so close to 100%, you can define the second one can be sort of interpreted as like how close is it to like the best path, like what's the how close is it to like the actual shortest path. Cool. Yeah. So the model, as I mentioned, is like an LSTM, where they feed in I think at each time step they feed in what is the coordinates of the goal here, the coordinates of the goal, and then the current coordinates of where the agent is, and then the heading, so like where is the agent facing. And they use like a reinforcement learning algorithm called DDPPO, which my knowledge of reinforcement learning is very low, so I didn't really look into that much. But if anyone has like an idea of what kind of algorithm that is. Yeah. Is it relevant? Do you think it's like cool to know for the paper?
I don't think it's really relevant. It's just common, somewhat called reinforcement learning algorithm. It's a lot of robotics and it works well.
Okay.
Yeah, I don't think there's a lot of detail there that's relevant. Good to know about that. If there was a different algorithm, you have a pretty good one.
Sweet. Yeah, so I guess this first part, as I mentioned, is probably not as interesting, but what they find is that these blind agents have like a really good success rate, 95% success rates in unseen environments, which is very close. Was basically like the same as another agent, which does have depth perception as well, which perhaps is like quite surprising that it can do as well in terms of success. I guess the biggest difference you can see is like the efficiency of how it gets to the end goal. So the blind one from this study is like 62.9% efficient, whereas the depth one is 83%. So there's like a huge jump in efficiency in terms of how it gets to the end goal.
This was all relative to a given time frame, right? You think that if you keep more time, that way it will do well, right?
Yeah, because I think past 100, I think they give them 100 after, or maybe it's 1,000.
2,000.
Yeah. Yeah.
2000 times 3,
2007.
Just on the point of the positioning as well, like, what's the purpose of the z-axis? Is that just for the?
Yeah, I was confused about that as well.
Yeah, because I mean, I can understand obviously they were moving up and down levels, which is I guess adds extra difficulty to it. But I think not to like throw it in if all you're doing is navigating a 2D maze.
Because I think one of the data sets is I think is 3D. So they mentioned a little bit like what data sets they use. They use 2 different data sets.
Sorry guys, I got it.
Okay. So they do 3D replicas of real houses, and then they use the Gibson data set and Matterport 3D. So I imagine that some of them have like some 3D component to them, but a lot of the examples they use tend to look like 2D examples. Okay. Yeah. Cool. So yeah, first one probably not so exciting. They perform really well. The task at hand, but not very like efficiently in terms of getting there. So the second experiment is looking at. So they note that these agents have these kind of behaviors where they have like the wall following behavior, and also like they try to understand like can it detect like collisions. So yeah, so they mentioned that this like the behavior is quite consistent. So a lot of the agents exhibit this behavior of following walls, and they give an example here. Well, both of these really, where like in the left example, you can see the agents kind of like sticking a little bit to the wall and going alongside it. And also in the middle one, you can see it's kind of going straight, but then it seems to be like sticking to the walls as well. So they hypothesize first, like why is it that they demonstrate this wall following behavior when they're trying to get to the point like as fast as possible? So it should be straight paths. So they have a hypothesis, which is that because the agent is that one's the second hypothesis, because it's in unknown environments, it's a behavior that's emergent in order to navigate unknown environments. So the first thing, well, one of the things they'll test is like, how can we show that this is the case? And then the second one is because the agent is blind, it doesn't know like where the obstacles are except bumping into them. So they say like, can it understand like when it's colliding like with an object? So for the wall following behavior, what they do is that when they train an agent in one environment with like one coordinate system, they find that the wall following behavior doesn't emerge, and they choose the shortest paths. But they do, unsurprisingly, like super bad on new environments because they just learn to memorize the environment they're trained in. So this points to the fact that like wall following is an emergent behavior to try to navigate new environments. And to test the first hypothesis, which is about collisions, what they do is they say like they take so at a specific time step, they take like t, they take the internal representation of the LSTM at time t+1, and they use that in a linear classifier to try to predict whether the previous time step was a collision or not a collision. And they achieve 98% accuracy on held out data, which interestingly shows that like in its internal representation, like collision versus not is like linearly separable. So they just use a simple linear model, which they point to strongly suggesting that the agent has learned some kind of collision sensing in order to help like navigate its environment.
What do you mean linearly separable?
Because they use a linear model on the internal like representations to try to predict whether it's a collision or not. And so a linear model achieves like 98% accuracy. So practically.
Linear separable means collision and non-collision.
Yeah, exactly. Yeah. And then what they do, this is actually probably one of my favorite things about the paper, is they apply like lots of different techniques to try to do like these kind of experiments or answer these questions. So then they kind of go a bit further in this collision detection and say, okay, we're going to have a linear classifier, but they're going to use L1 regularization, which encourages like sparsity in the features. And then they select the top 10 neurons that are, from this like linear classifier, which, reduces dimensionality by 99.7%, but still achieves like near perfect score. And then they plot those, the points using TSNE, which looks something like this. So what they find is that it's like quite clear that it learns these different like actions basically, or it can like classify almost the previous actions internally, whether it's like I've gone forward and I collided, I've gone forward and I'm fine, or I've turned and there's like no collision. Because turning doesn't create any collisions because you just turn like on as you stand. So yeah, that's another cool thing. So it seems that the agents are learning how to like understand this, like whether they've collided or not, as a way of like navigating the space.
The overlap is probably due to coming in at an angle where we just slightly graze the wall.
The agents are circular, so the collision is always curved.
Doesn't it say it only knows how much it moves, right? At one step, so that it would move just, any side, right? It would still probably get most of it.
What do you mean?
You would think that if moves and collides, it has a 100% separation, right? But if the wall, it's not a big guy, it just might barely move, and all it knows is how much to move, right? So it might still move like 0.245 meter rather than 0.25 meter, and
Yeah.
and that might have that might make it so that it's not really that clear whether it actually collided or not.
Yeah, interesting. Yeah, because you would think that it would be very obvious.
That would require there to be like a friction, like
It doesn't
a
sound like that
simulated
friction.
environment.
But the walls only for buildings or do you have like angled walls?
No, they have angled walls, I'm pretty sure.
So it can be like how usually.
But the agent is circular, so
Yeah.
it's always like a point on the circle that's colliding. So the impact would always be like towards the center of the agent, no matter what heading it has.
It would then just stop. But it wouldn't know that it stopped, it would only see that it doesn't update it as much as otherwise.
It hasn't moved much, yeah.
Do they have a width, or is it like the agent has a point?
They have width.
Is there?
Yeah, but you think. Oh, that's what I was going to say. Yeah, one limit say, or like thing they mentioned at the end, but I think is also quite an important point, is that in all of this reminds me of the coordinate system, they have no noise in the measurements as well. Whereas like if you think of like real life robotics, there'll be some kind of, well, Peter will be able to say better, but like there'll be some kind of noise in the sensing, right? So this is like, it knows its perfect coordinates at all times. Yeah. Cool. So yeah, the third experiment is understand like what part memory plays in these agents. So what they do, and I find this part a little bit confusing at the end, but so if anyone, I'm going to explain how I interpret it, but if anyone understands differently, please let me know. But I think what they do is that they train the agent normally, and then they put the agent in like a new environment, and they play around with like what happens if we basically restrict how many time steps before it sees in the LSTM. So they set everything from t minus k to t, and they have this parameter k. They pass the like internal LSTM representation, but everything before that they set to just 0. So they like forget it. So what happens is obviously when it only has access to the previous time step, it does like really, really poorly. I imagine it's probably just like gets stuck in a loop or something. And you see the performance, both in the success rates and in the efficiency, goes up and seems to plateau at around k equals 1,000. So what I didn't understand quite is that they say at the end that they, in the appendix, they train agents to operate at a specific memory budget. And they say they find that a budget of k equals 256 is the largest they're able to train based on like compute requirements. But I don't understand how they get to like then k equals 1,000 here.
That's at test time. So they're at test time, they're using a larger budget than at training time. So for example, at test time, you could be showing the last 1,000 observations, whereas at training time, you can only show 256.
Oh, okay.
So it's actually the whole insight is that it's able to extrapolate to longer, like it's able to take into account longer horizon information than what it's trained on.
Interesting. Okay. Yeah. Okay. So they train on. So what they show in the appendix actually.
How does it work in practice? Do you depend on?
So it can take into account a sequence of any length. And so what it's saying is they take during training, they take the last 256 observations.
They break it into more parts.
Yeah. Well, each time they just take 256 observations,
Yeah.
which is a really small vector. I mean, matrix, it's 256 by 5. So,
Yeah. So here they show them like the performance and memory length for training. So yeah, okay, now I understand. It seems it's cool that like they can, yeah, like you said, it can go up to 1,000 and still improve performance at test time.
Would you think that that depends on the environment that it's trained on? Let's say that this over the certain ratio compared to the step size they take, right? So you can think that you divide one by the other, you get something that it's a really the order of magnitude at which these things might.
Yeah. Yeah, they do say they say something that like the 1,000 steps is roughly like 89 meters. So I suppose it's like the size of the environment maybe plays a part in how much impact that has. So summary of this experiment is that memory is useful. And then this one I think is the next ones I think are the most interesting ones. So what they're showing here, or what they try to show, is that does memory play a role in improving like the performance on like the existing environment? So they then differentiate between an agent, which is like the primary agent that we've been dealing with, and a probe. And a probe is effectively the same, exactly the same as an agent, except it's initialized with the last time step of the agent, like the last representation time step of the agent is the first one that's passed into the probe. So again, I think, like, anyone correct me if I'm wrong, like if I've misinterpreted, but I think what happens is the way this probe network is trained is that the agent network is trained first to like traverse it. It takes the last representation at time capital T, and that gets passed as the first input into the LSTM for the probe, and then the probe gets trained effectively in the same environment.
When you say trained, is it actually still trained here, or is it already like a test environment where it just runs through and they sort of build up the memory rather than actual any weight training?
So it does mention somewhere that it's trained. Yeah, because they compare, so they have these, they have these 3 different probes. So one is like the probe is initialized with like 0, and the second one is that it's initialized with, oh, sorry, no, that's different. That's just whether it's the agent's been trained. It could still be trained.
it's definitely a trained agent.
Yeah,
The probe.
The probe. Just because I don't think that you could initialize a random neural network and be able to do that.
Meaningful steps. Yeah, I think so. I'm pretty sure it says somewhere about like because it mentions that like everything is the same, like they use the same architecture, same training. Yeah, I'll find it now. Might be somewhere else, or it might be in the appendix.
Yeah, well, it says results of our trained probe in our 3 configurations.
Yeah. So anyway, what happens is, so they train this agent, and this agent traverses the environment, and then the last representation of that agent is fed as the initialization of this probe. And what that leads to is the probe is significantly more efficient at navigating the environment than the agent, which seems to suggest that in traversing that environment, there's value in the memory of that agent in like having a completely new like probe, also exploring it. So
How do they show that it's more efficient?
so that's they do like a path length. So you do success weighted by the inverse path length.
I can put it in an abstract, right? So it does, there's follow different strategies, so to speak.
Oh, I see. It's that there's like in that table, there's like a 13% increase in SPL.
Yeah, exactly.
Okay.
Exactly. Yeah, and they show that it's not just about having, so importantly, it's not just about having like initialized by an untrained agent that's explored the environment. Like it makes it different that the agent was also trained in that. I guess it seems to build better like representations probably of environments than the untrained agent would. Yeah, which is what they mentioned here. So they test whether like simply being encoded by an LSTM with random parameters, whether that provides some kind of inductive bias, but it seems to perform the same as like having all zero memory, so no memory at all. And the trained agent outperforms massively like in terms of efficiency.
But I think it says something that an untrained agent gets 92% success rate. Like about the task essentially.
It's the probe that achieved 92%, I think.
Yeah,
It's the probe that's initialized with an untrained agent, but then the probe is trained.
Sorry, okay, I see. So it's have like a random explorer at the untrained.
Yeah, exactly.
Okay.
That wouldn't be a great experience.
So it's like all LSTMs can navigate all the like environments almost near perfect. Yeah.
Yeah, there is no occasion that like, for sure, I guess there's no experiment which you would have like 90% of normal success rate. Think of like you put the coin split the person, like how do you get an experiment with a 90%?
Well, if you have one of the reinforcement learning algorithms, like the theory behind why they work in part is that they will, if you have a bounded environment, then I think even if it's infinite, but I think definitely if it's a bounded environment, that you're guaranteed to explore every single step of it using the exploration process that you use to learn. So it could be that like, I wouldn't be surprised if on a long enough time horizon, any agent would have be successful, even if it was moving randomly. In fact, you probably can prove that that's true.
Yeah.
But I guess you don't, it doesn't know when to stop.
Wouldn't it learn from like the reward?
Yeah, I guess it would learn. But yeah.
I also thought that the debug algorithm they seem to be less efficient than it could be, right? So it always go the wrong rather than whenever it needs to walk fly next to it.
Yeah.
Also, that would be then.
Yeah, oh, great. So yeah, the picture shows the blue line is the trained agent and the purple line is the probe that's initialized from using the memory of the trained agent. So you can see it's like taking shortcuts basically. I think this is the final experiment that they do, which is.
I think it was something else where they tried it the other way around.
Oh, yes.
I thought that was pretty cool. That really shows something that reverse the task.
Yeah.
Still works.
Yeah. Targets a source and also like kind of has exactly the same performance or very similar performance. So yeah, it also works in reverse.
I was thinking that the probe agent is, if any, like it doesn't sound like the behavior of the initial agent is learning the map. It seems like like a set of, like an algorithm, like the bug agent, but the probe agent must be the one that's actually running the map. Because it's
Yeah.
able to navigate more efficiently.
Yeah.
Exactly, the user agent learns the strategy, but it is bringing a map that can be exposed.
Because I suppose the agents, it gets dropped in a completely unseen environment, so it has no map. So it just has to learn to navigate completely unseen spaces.
But I'm just saying the behavior of the probe doesn't necessarily suggest that it, that it's learning a map. It's like collide with the wall, move along the wall, collide with the wall. So that's not necessarily showing map creation, but the probe shows clearly that it's.
And it must be that because you get pushed around, right?
Yeah.
It was only one direction, you could still argue that the number is a lot of driving functions, but clearly it seems to be not the case. Why it's actually very, very small.
Well, so speaking of maps, so the next question they try to answer is whether the agent is building some kind of map of the environment as it's navigating it. So the way they test this is they say, okay, given the like final representation of this agent, can we train a decoding network to predict, given like a grid, whether whether somewhere is like a free space, as in you can move around, or whether it's not, like it's not movable. And so then they made predictions within like 2.5 meters of the agent, because agents wouldn't really be able to know anything about like spaces they haven't immediately traversed. So yeah, so then what they do is they compare these like maps to ground truth and use the interaction over union to compare. And this is these are the results basically. So in like the A and B on the right, you have the ground truth. So you have in blue like the path that the agent took, and then on the left is the ground truth of what's navigable and non-navigable, and then on the right is the prediction. So it shows that it's kind of building some like idea of like the spaces it can navigate as it moves across the environment. One of the things they highlight in the paper is that it understands like corridors. So when it's like following a wall, it tends to predict that there's a wall on the other side as well. So you can see like on the left one, as it's like navigating this wall, it says, okay, probably there's like a wall on this side where I can't also navigate, and it seems to like do that quite consistently across here as well. I find it interesting that like it couldn't, like there's some gaps where it navigates, but it says it's not.
Probably because of that strength. It's collisions that actually make it learn this thing, right? And then when he doesn't collide, he has no information on whether there's a wall left or right.
True, because here I guess it's not like sticking to a wall,
Yeah.
so it just doesn't really like understand so much around it.
But if it sort of touches the wall again, then it knows it must be a wall.
Yeah, that's true. So I suppose it suggests that then it's like building, by navigating close to like walls, it's learning to build maps, a map representation based off that, based off how it navigates by following walls. But this is I think one of the main points of the paper, which is really like, this shows that there's some emergent like map like behavior in the representations, given that it's possible to like construct these maps based off of the final representation of the agent. And this is for like unseen locations as well. So this is like it navigates an unseen location, it can generate a map for it. So
There must be so many cool applications. Underwater robots or
But there's a really we kind of talked about this, but this really key thing to observe is how perfect and simple this environment is. And that's because the paper is just trying to show it as a proof of concept. But like extending any of this, like reinforcement learning underwater with real robots, we're not close, in my opinion.
And funny bit was also that the moment you give it sight, that you would argue you want to do for insurance reasons.
Yeah.
I think it loses the ability to do the next step. So,
Yeah.
yeah.
Yeah. Well, this is quite an interesting thing is that like it says they couldn't perform the same thing on sighted navigation agents. And I think they mentioned this as like further work for exploration, but they suggested it's because navigating with sight is too trivial for the agents to even bother building map-like representations. It's like it's too easy. So yeah, it doesn't do this kind of like
In this
behavior.
environment, it's too easy.
In this environment, yeah.
Can they add random noise to the simulated environment?
Yeah.
And then,
Yeah.
They can add random noise to the observations of the positions.
But we don't do it here.
They don't do it, no.
Because that's not what the paper's about.
They sort of do it by the starting position by shifting your coordinate system. So you could argue that there might be such a thing like a classification that the agent learns which of these, I don't know, 1,000 sample environments it's currently in, and then they know that we're going to go there. I don't think it happens here.
Yeah, so I guess an interesting thing would be like, I don't know if there's data sets, there's open data sets with more complex environments, but I suppose you could add noise as well. Yeah. And then experiment on sighted navigation agents.
There's a whole, there's a simulation environment called Mjoko, which is like a physics environment that is used a lot in robotics. You have to pay to use it, which isn't great, but it's like, for example, DeepMind, most of their experiments are using Mjoko environments. And then you can do a lot more. Like you can simulate noise and sensors, you can simulate noise and observations. Those are the same thing, but like you can do a lot of that kind of stuff.
Yeah, then the last thing they look at is mapping so is the mapping task dependent? So what they say is like, is it learning what it needs to learn to perform the task, or is it just learning maps like because for some reason? So yeah, they basically given like the internal state at a time t, they train a network to try to predict where the agent was k steps into the past. And what they show is that it shows that the agent forgets excursions, and they manually label excursions. It's like basically where an agent's just gone on like a loop, but it hasn't brought it any closer to like the actual target. So in the left picture, you can see that like the excursion is marked in red. So it's basically showing that like that's an excursion because it's going completely astray and then coming back and then going to the state. And in blue is the like predicted chance that the agent has like visited that step in the past. And what they're saying here is that in this specific example, there's a much lower like area of probability around the excursion than the initial path that the agent took, which they take to suggest that it's not like remembering, or like the memory is not as important in the places that it does excursions versus the paths that it takes to lead to the actual end goal. And they then they show this by like doing the like past, like predicting the steps in the past and showing that the error is always greater for excursions and exits than non-excursions. So it seems to place a greater emphasis on remembering, like direct paths.
It's kind of funny to think about why this would be, that it wouldn't forget its own past, at least in a further distance, right? Because either that information is not useful anymore once the trained agent moved closer to the And unless there are cases where it has to sort of come back to the beginning and then try it's weird.
It seems interesting. So it's like the error does increase quite a lot as you go back into the past. So it clearly remembers more like what came before. But then if you combine this with the other experiment on memory, like 1,000 steps, like or like adding more steps still contributes to better performance. So clearly there's some value in understanding what you were doing 800 steps ago. But yeah, I wonder why.
Maybe the environment sort of loopy or so that you know it's.
Yeah, or maybe like because it does go on some, maybe because it goes on some long excursions, like it needs to remember, like when it comes back, it's like, okay, I've been here. This seems familiar.
I was wondering, like, is this the best way of going with this like random walk, or is there any other way that like this can be done with a higher success rate?
This specific task.
Yeah.
Well, the success rate seems pretty high already, so it'll eventually get there.
Like with less repetitiveness for it to come to that point of maybe like a faster way.
Yeah.
It looked like that when you increase the memory that the path length plateaus off, right? It would suggest that this sort of becomes optimality given the tensor constraint you have, right?
Yeah, here the SPL seems to plateau. So I guess they do show that. So they keep like bashing this whole like cited when it has depth, but the reality is when it has depth, it performs much more efficiently, like the task at hand. So they show it up here. When it has cited, the SPL jumps to 83% compared to 62%. So it's quite a big jump. So even though they shit on the cited agent a lot, it's like it still does like more efficiently.
The only time it might do, well, actually, maybe do worse is if there's like a, maze where there's basically a wall blocking, like right next to the goal that's blocking it, so you have to go the long way around. Because it would probably wouldn't logic to go straight to the goal, but it's not the right way to go. Whereas a blind agent might sometimes go the other way without knowing.
And set it off in like a messy kid's room. So there's toys everywhere. Yeah. Cool. So those are like the series of experiments that it performed. There's a whole, if you're curious about any particular experiment, there's like an appendix section on each of them with more like examples and more details about how they perform these experiments. But I guess to finish off, they point to like future directions in this kind of area. So yeah, suggest that like maybe considering like either explicitly or implicitly biasing agents towards learning some kind of internal representation of the space may improve performance. They mention that they examine ground-based navigation in digitizations of real houses. So they say it limits the agent to a 2D manifold and induces strong structural priors on environment layouts. As such, it is unclear how a result generalized to a drone flying through a large forest. Which is kind of to your point earlier. I don't understand whether it's 2D or 3D or like what this
The
suggests.
reason why there's a Z-axis is just because the simulator they were using provides it, like, or something like that. It just kept that there.
Really? Okay. Yeah.
Easier than trying to hack it around it not existing.
Yeah, I think you could easily take it out of the vector, but maybe they're like, why do work you don't have to do? Very little work.
We'll just add it in anyway.
Do you think it's why when they're training, they would only go, exercise would only be 2 by 6? Because it seemed drastically large.
Not sure. It might have to do with the memory capabilities of the GPU, like how big the GPUs were. I don't know, because when I'm thinking about reinforcement learning, you're usually using like bootstrapping, which means that you're only looking at one step at a time. So you only have to back propagate through one step at a time. Oh, no, because that's 256 observations. So actually, yeah, that could be a lot of, no. I don't know.
Needed to train the model. We were unable to train for a memory budget longer than 256.
Why don't they use anything besides an LSTM?
LSTM is probably the most efficient in terms of memory usage, though. So like a transformer would use so much more memory.
Yeah.
Just the 256, is that the length, the H and C vectors, or?
It's the length of that's the,
Vector.
yeah, that they've been into the end, right?
What is it?
How come they don't have certain GPUs? I mean, I
They
think
did, they trained on 16 GPUs in parallel.
it's not like that much.
What?
Maybe.
I don't know. It might be that they were like trying to, make,
Maybe.
they were just like, we just want to do a quick, maybe it was they chose 256 because they wanted to make it quick too. So they wanted to have like a large batch size.
Yeah.
I guess that, so there's probably, I don't know about them in particular, but I know in our area, in the like networks measurement space, when you come in from like a large organization like Meta or Facebook, the academics kind of frown on you being like, I've got this million GPU cluster, and here's all these amazing results that we got. Like, isn't it a shame that you could never do this? So I don't know, they maybe limit it down to like not piss anyone off.
Yeah, but I feel like now we're at the point where universities are just going to have to scale, otherwise they're not going to be able to produce like meaningful, useful results.
Oh, for sure, I agree. I mean, we've got friends at Facebook that work in like the measurement side of things, and they've had papers rejected. And like reading between the lines, it's like, oh, well, it's unfair that you have access to this data.
Yeah.
Really?
Yeah, so I don't know if it's the same in like this sort of space, but yeah, it's
I like that.
it's true. Like some communities are a bit, I guess, old school.
Because if we don't know what what machine learning companies are doing, it makes it even higher barriers to entry for other people.
Yeah.
So, because maybe we don't have access to the data, but at least we'll have access to the IP.
Quite interesting collaboration.
Yeah. One thing I said before, it's not related to the paper, but I just looked it up, and Joko is free now.
Oh, it's free now.
Because anyone can do research.
Your next paper.
Yeah, how are we going to tie end time work into robotics?
You go and mitigate risk in the field.
You're making it wrong.
Yeah.
The survey, the construction
Exactly.
site. Yeah. Yeah, cool. I mean, as I said, I think they add one sentence that the fact that they don't study actuation noise, which I think is probably like worth mentioning. I imagine.
It was automatic.
I did it.
You unmuted me.
I know I muted you.
Oh.
I don't know who unmuted.
Aren't you unmuted yourself?
I wasn't even there. I would be really interested to see, because that, for me, one cool thing about the paper is this idea that you can go from like a sequence of collisions and movements stored in like this internal representation to a map. And I'm wondering, I feel like maybe that points to how you could bias a model towards learning internal representations. I don't know how you could abstract it so it's generally useful, but I feel like there's probably some kind of shared structure between navigation and map creation that could be like something that they work on. Yeah.
Yeah, so how the map is done right now, and make shortcuts. So I don't understand how people could do it parallelly to know there's nothing here for you to do there.
Yeah.
There's like a saying in machine learning that's something along the lines of whenever machine learning does something new, like for example, ChatGPT, everyone says that it's becoming like as intelligent as humans. But the reality is usually just that the task that it's learning to do is more predictable than you think. You know, there's a lot more structure in it than we think as humans, because we don't see it. But if you have a model that does, so maybe there's a lot more structure in the problem than we can understand.
I mean, probably there is, right? Because you have the whole motivation behind it that animals with lots of different sensory inputs can navigate effectively. And so it's like, well, surely there must be some patterns to learn here.
Everything in life has some patterns, I guess.
Yeah, exactly.
Next time we do kilo session.
Yeah.
We tried that once. We did the
Philosophy
Chinese,
paper.
we did the Chinese room.
Yeah.
Which is like a famous philosophical paper in the 70s on it now, but it didn't go that well. We'll stick to technical things.
From Mao, you said.
What?
From Mao, you said with Chinese roots, you
No,
said?
no, it's called the Chinese room.
Yeah.
It's written by like a philosopher in the 70s
Mm.
at a US university.
Okay, right. Once you mentioned 70s and Chinese, Mao didn't came to my mind, so I thought like Mao.
Yeah, was it like a lot of the people in the discussion or was it?
Yes. We provided two resources. One was the paper, and then also the discussion by this professor called Gerard, who like talks about the social, ethical, and economic impact of AI. Like that's what he studies as opposed to the technology itself.
Maybe we should do topic about that.
It sounds quite interesting, but I can imagine it being difficult actually.
Traffic days.
Yeah.
Right?
Assign people to
Yeah.
decide.
Meeting with like convergent social sciences, meeting
We have it.
Yeah. Yeah. Thanks everyone who joined on the call.
Thank you.
Lead voice. Should go for